So good evening, everyone. My name is Ayush Goel, and today I'll be covering the topic from NAND to Tetris, building a modern computer from first principles. So good evening, everyone. Right now I'm in my second year of BTech Computer Science, and I'm studying operating systems. In operating systems, we are taught how to make computers, not actually computers, but how to make computers workable. Computers are just physical objects and hardwares which do not have any use until and unless they are provided with an operating system. So, in this particular video, I'm going to tell you about a project from NAND to Tetris. In this project, we build a modern computer from first principles, and these principles are actually Boolean logic, logic gates, and very small parts of a very big computer. So we can just dive into it. So first of all, the overview. So in this particular video, we are going to learn about how to make a computer from scratch, how to use basic Boolean logic to create computers, learn about the NAND to Tetris hardware simulator, learn about logic gates in Boolean algebra, learn about HDL, which is the hardware definitive language, HDL-based chip simulation, and basic concepts of the operating system. So let's get started and cover each of these topics. So first of all, how are we going to make an operating system out of this our whole course? First of all, we need the computer architecture, like what kind of computer architecture we are going to work on. Are we working on a Harvard machine or a von Neumann architecture? Then we will need to learn about CPU, RAM, and chipset. What kind of a CPU we are using, what kind of RAM we are using, and what chipset we will be working on. Thirdly, we will learn about elementary logic gates, and these logic gates are together combined together to make complex structures, complex circuits that solve difficult questions, thematic problems, and help the computer in working. They are the basic building blocks of computer logic gates. And finally, via electrical engineering, we convert this logic to hardware, to actual printed circuit boards that we usually call as motherboards. So basically what motherboards have, they have small logic gates. So before actually printing these logic gates, we need to create a software simulation of this logic gates. So this is what exactly we are going to do in this particular course. So what is Boolean logic? We must have heard about Boolean logic somewhere else if we are in computer science. So Boolean logic is a type of algebra that is created by operating the binary system. In the year 1854, George Boole, an English mathematician, proposed this algebra. This is a variant of Aristotle's proposition logic that uses the symbol 0 and 1 or true and false. Boolean algebra is concerned with binary variables and logical operations. So basically, Boolean algebra consists of only two type of states, that is on and off, that is 0 and 1. And together with only these two states, we make complex circuits, complex designs, complex computers, complex hardwares, and finally printed circuit boards. In Boolean logic, we have three basic identities, three basic operations, that is OR, and NOT. What the OR does is it chooses between two data. If one of the values high, then it gives a high output. And in AND, if both the values are high, then only it gives a high output. And in NOT, it just inverts the value. For example, for a high voltage input, we will get a low voltage output. And for a low voltage input, we will get a high voltage output. We're going to learn more about this in this particular project and in this course. So let's move forward. So first of all, what is the basic Boolean operations that I just introduced you to? The first one is, I'll just put my laser pointer here. So the first Boolean operation is X and Y. So and what we do in and is that I'll give you an example that Rohan went to the market and bought fish. So what happened here is that Rohan went to the market, which is a definitive statement, and he also bought fish. He also bought fish is another definitive sentence. So similarly, in X and Y, when both the values are affirmative, then we can say the result is affirmative. So for example, X, Y, if both the inputs are 0, 0, then the answer will be 0. If one input is 0 and the other one is 1, then the answer will be 0, because we are saying like, did Rohan go to the market? And did Rohan buy fish? If the answer is Rohan went to the market but did not buy fish, then the statement is not correct. The task is not completed. So that's why the output is 0. Only when both the statements are true, we will have a high output. That is a true output. Now, the OR gate. In OR gate, what we do is, if we have or is basically any one statement should be high, and we can say, okay, the task is done. So for example, if I ask, did Rohan go to the market or Rohan bought fish? So in this or statement, if one of the answer is correct, then we can say the final answer is also correct. So in the truth table, you can see when the input for both X and Y is 0, the output is 0. And when one input is high, we can get an output high, that is 1. And finally, the NOT gate. The NOT gate is an inverse gate. It helps us inverse the data or whichever is being input into the gate. So for example, if the input is 0, then the output will be 1. And if the output is 1, if the input is 1, then the output will be 0. Now the basic Boolean identities. When we use Boolean algebra, the basic two states, we need identities to solve mathematical equations, mathematical problems, and this helps us a lot in mathematical uh, actually problem solving. Now, so for example, the first two identities are the commutative laws. That is, X and Y is equal to Y and X. It doesn't matter if you change the order, the value will be same. Secondly, X or Y is equal to Y or X. So it's pretty much confident to say Boolean identities are Boolean algebra is commutative in nature. It is also associative, that is X and Y, X and in bracket Y and Z will be equal to X and Y with in bracket with and Z. So associative laws work on Boolean algebra as well as distributive laws. And finally, another theorem, De Morgan's law. What happens here is, so if we say that we do a NOT gate on X and Y. So basically X and Y together are done first and then a NOT that we inverse the gate. So we can write this in another form, not X or not Y. So this is the De Morgan's law. It is a basic identity that helps us a lot in creating circuits. Now the elementary gates are NAND, AND, OR, and NOT. So gates are nothing but the logic in a symbolic form. So for example, for the first one, NAND, NAND is nothing but the inverse of AND. So if I say A is 1, B is 1, then the answer for AND will be 1. But in NAND, the answer will get inverse and the answer will be 0. And OR and NOT gate works the exact same way I just told in the previous slide. Now, we know about gates. We know about Boolean algebra. What is HDL? HDL is hardware description languages. HDL are languages that help us to simulate this Boolean algebra, Boolean circuits on the computer and before creating them into hardware. So HDL is a functional and declarative language. An HDL program can be viewed as a textual specification of a chip diagram. The order of HDL statement is insignificant. So for example, in this particular program, we can see that we have created a HDL program for an XOR gate. Now, XOR gate is another kind of a fundamental logical gate. It's actually not a fundamental gate, but a subtype of the OR gate. Now, I have an example here about a XOR gate. So this is an XOR gate. XOR gate returns a high input whenever the number of high inputs are odd. So for example, if A is 0, B is 1, then the output will be 1 because the number of inputs that are high is odd. Similarly, in the second case, A is 1, B is 0, the output is 1. But finally, in the last one, when A and B both are 1, then the output is 0 because the number of high inputs are actually even. So now we will jump into the hardware simulation of the Nand to Tetris software. I'm going to open the software here. Yeah. So this is our Nand to Tetris software, hardware software. Hardware simulation software. So in this particular software, what we do is we can just, for an example, I'll open a simple program. I'll load a chip, for example, AND gate. Yeah. So here you can see that this is the HDL code of our AND gate logic. So we have an AND gate, output 1 if A is equal to 1 and B equal 1, otherwise output 0. And then finally we have the chip. So this is basically our uh, AND gate on hardware logic. So I can show you the example. So for example, when A is 0 and B is 0, the output is 0. If I turn A to 1 and then simulate this code, so 1 minute. Then the output is also 0 when I make this 1. 1 minute.